This lecture is going to be about the concept of related rates. And so in the homework, these are the problems where we have a pool filling up, where we have a plane traveling with a distance relative to something on the ground. This is a ladder sliding. So a lot of these related rate problems have all involved a movement of something. So when we're filling the pool, the water is going up. If we're draining something, the water is going down. If the plane is moving relative to a point on the ground, we have a triangle formed because there's movement in both the y-axis and the horizontal. So related rates are all about movement, and they're typically differentiated with respect to time. So in this situation, we're just reminding ourselves that we have a circle. A circle has a radius, and I can look at the way that the hand on a clock moves relative to time. That would be considered a related rate. So we can look at that movement using the circumference formula and looking at that as an example of a related rate. So the procedures for a related rate problem are going to be the same, but they're going to differ slightly from problem to problem. So you always want to read the problem very carefully. And when I do my first read, I underline all the numbers, and then I sketch what's going on and label everything on my sketch. Now with the related rate, it's important that for every variable you're given, you're going to be differentiating that variable with respect to time. So some of the numbers in the problem might not be, for example, the ladder falling away from the wall. They may give you the height of the ladder, but they may tell you it's sliding away from the wall at a rate of 2 meters per second. That's a derivative, not an original value for the formula. So really look at the units of which you're given. If you're given something with a unit of time involved in it, it's probably what the derivative is at that point in time and not the original function. So you're going to identify the rates that are given, the variables that are explained, and we want to tie it all together with the basic relationship among the variables. So if my pool is filling up, what's happening is things are changing, is the volume is what ties the length, the width, and the height together. If my ladder is sliding away from the wall, the Pythagorean Theorem is tracking that movement. If I have an airplane relative to a point on the ground, it forms a triangle. So we're looking at the Pythagorean Theorem. So you've really got to look at what formula is going to encompass everything that we're looking for within the problem. Then you're going to differentiate the problem with respect to time. We're going to substitute all the variables we know, all the rates that we know, and then solve. Make sure you really evaluate your units. Make sure if it's a derivative, your unit should be some unit of length or measurement per time. If you're looking for the original value of a variable, that would just be meters, seconds. It would be 1 unit, not a unit per time. So here's an example where we have a plane flying relative to some point. So my plane is approaching the airport. This plane is approaching the airport. And then we have this dz dt. So if I'm looking at these, I have movement and changes happening across the entire triangle. And what's going to tie them together is the Pythagorean Theorem. So because I have 2 planes moving, I do have movement in the y. I do have movement in the x. And then my hypotenuse appears, if they're moving at the same rate, it could potentially be not changing, which would mean dz dt would be 0. Really look at the word problem and determine if something is not changing. Another example of this is a pool. So the length and the width of the pool aren't going to change. The height is going to be what changes. So really evaluate things as they change. So here, if I'm working with the volume of this and I'm differentiating this, I'm going to have to utilize the product rule. I know that R is 3H. So if I differentiated this as it is currently, I would have to do the product rule with R squared H. So I'd have 1/3 pi and then a bracket 2RH plus R squared close bracket. It's typically easier to go ahead and replace R squared with 3H so that I get 9H squared times H, which would be 9H cubed. That just takes that extra variable out so you don't have to do dr dt in that problem. So we want to make sure we work smarter and not harder when it is possible. Another thing you'll notice is that the radius of this is not going to change as it moves. So really, when we're taking that derivative dr dt, is it really going to gain us much of anything? Now, here we have a hot air balloon, and it's going up. And if you look, it appears this is not changing. There's no arrow happening here, but the distance between the two people is changing. So when I do the Pythagorean theorem, if I had x squared plus y squared equals z squared, my x squared is going to be 200, or my x value is going to be 200. But when I do 2x dx dt is 0, so this term goes away. Then I get 2y dy dt equals 2z dz dt. So when we're looking at these types of problems, we're tying them all together. We're looking at what's not changing, and then we're using it to describe that. Now let's say this balloon is rising at 2 meters per second, and this is 400 meters. So, and I want to know the hypotenuse. So at that point, I would do x squared, paintbrush. Let's pull up something so you can see what we're doing. So if we call that let's put these measurements down here. So if I have 200, and we're assuming that this balloon is rising straight up. So that means that dx dt would be 0 because it's not changing on the horizontal. Let's say that this is 300. And let's say that dy dt is 2 meters per second. And they would ask you, how fast is the balloon moving relative to the person? So I'm looking for dz dt. A lot of times in these problems, you're going to have to solve for the hypotenuse of the triangle. So I'm going to use the Pythagorean theorem. 200 squared plus 300 squared equals my c squared. So I would use that to solve for c. So I would get some really large numbers. I would get 40,000 plus 90,000. So I get 130,000 for c squared. I can take out 10. So I'm going to get 100 square root of 13 for z. So when I differentiate this, I'm going to get 2x dx dt. So I'm just differentiating the Pythagorean theorem, plus 2y dy dt equals 2z dz dt. Now, dx dt is not changing, so this term goes away completely. And then I'm going to have my 2 times my y value of 300. Then dy dt, which is 2, equals 100 square root of 13 times 2 times dz dt. So I'm going to get, let's see, 2, 4, 1200. I'm running out of space. I know this is hard. Equals 200 square root of 3 dz dt. So then I know that dz dt is going to be the 1200 divided by 200, which is going to be 6 divided by the square root of 3. So I'm going to have 6 over square root of 3 is going to be my dz dt. So really with the related rates, if you get the formula that ties it all together, that's what really brings things together. Here's another example. If I'm looking at things with this triangle, if I'm given my x is 200 and my y is 120, I can use the Pythagorean theorem to solve for z. This is the most common application of the triangle, but occasionally they may ask you for the change in the angle, so cosine theta, at which point you would know that you're differentiating cosine theta. But we can also find the value of cosine theta by applying our trig properties and doing adjacent divided by the hypotenuse. But the most common problem you're going to see is going to involve that hypotenuse right there. So that's how we look at related rates. Really make sure that you're differentiating the right formula that ties everything together. Make sure that every variable that you differentiate, you put with reference to time. And then when possible, like in this one, the working smarter, not harder, is to go ahead and replace r with 3h before you take the derivative. You'll get to the same place if you take the derivative first, but it's not going to be as quick.